Okay, so I want you to tell me something here. I want you to tell me.
Grapes are purple.
What's that?
It could be green. You said tell me something.
No, no, not that though. I want specific. I want you to tell me what is going on. If I drop this pen, I want you to make a prediction what's going to happen.
It's gonna hit the ground.
Hit the table up. Hit the table, then the ground.
Okay. Okay, so hit the table. Okay, how come? What happened?
Gravity.
Oh, gravity. So what's that? Okay,
Okay,
somebody raise a hand and let's get an answer. Yes, sir.
It's about attraction between objects.
Okay. That's attraction, but why? I mean, okay? That's it. You're right. Gravity is something that we would define in physics. It's what is it? I mean, is it a?
Because both objects have energy.
I mean, not exactly. I mean, there has something to do with it at some level.
I was gonna ask. Put it out there.
So I mean, describe gravity then. What is gravity?
It's a force.
It's a force. Okay, what's a force?
The force
Well,
of gravity.
A push or a pull. Okay. Okay, sure. So
It flows through us and is around us.
you guys have kind of skirted around it, but you've told me that in terms of this vocabulary word you just gave me, a force, gravity is one of those things. It's a force, and it acts between objects that have what? Mass. Okay. So what is this? Gravity is now acting between the pen and what?
The dark side,
Between the pen and what when I drop it? What is it? Yeah, the Earth, right? It's falling towards the center of the Earth because the Earth has a lot of mass. The pen doesn't have much mass, but the Earth has something like 5.8 times 10 to the 24th kilograms of mass. Big mass, huge mass. And so it creates this gravitational force. But how? What's causing it? Are there some kind of, there's no strings here.
Magnets.
It's not magnets.
it's there.
But
Because science.
I want a real answer though. Can you tell me, and seriously, can you tell me why is it doing that?
Because it's massive bigger.
Okay, but why? What's causing it to happen? You labeled it a force. What do you think, Matthew?
Gravitational pull.
It's gravitational pull, but why? What is a gravitational pull? I mean, it's a force. But can you tell me what the mechanism is? Why does it happen?
Is it because it's spinning around the sun and that's basically the force?
No, it's not.
It's just there. Let's just like say that it's there,
So-
and we just will live with it.
Okay, so you guys don't have an answer for me, in other words.
Can I look it up?
Yeah.
Well, you could, but that's not going to help you today. Because I'm going to tell you, it's going to tell you the same kinds of things you just told me if you look it up.
So there's no reason.
No, there is a reason. But we're going to leave it for now. Well, you guys, you can't answer that right now, is what we come to, right? I mean, it's you know how it works. In physics, we have a bunch of equations that when you're all taking my physics class later on in your careers, which I expect you all to do, you're going to be able to make a prediction. If you want to tell me, for example, how long it's going to take to get to the ground, you're going to know to use this equation.
Not lots.
No, it's DO Vought plus 1.
Where G is the acceleration of gravity.
Oh,
That's it. V naught is initial velocity. But anyway, that's a kinematics equation. You guys will learn how to use that in the first couple of weeks of our physics class. But even that only tells you, it makes predictions. It's a model and it makes predictions about, based on some measurable quantities, what's the behavior of the pen going to be when I drop it. It says nothing about why it's happening. Right? Why it's happening is still a mystery to us. We've got a model that explains it, but why? Okay, so I'm going to leave it at that for now. Let's change subjects and talk about geometry for a second. What is just a quick review, what is the sum of all the interior angles in a triangle?
180.
Okay, so if I just, go out to, let's say that I'm the ocean, to make it really convenient here. Let's say that on a perfectly calm day, the surface of the ocean froze over, and I'm just going to walk on the surface. And so if I pick 3 points on the surface, and I walk do this. So I'm gonna start with this point right here. I'm gonna walk out to here. I'm gonna walk maybe out to there, and then I'm gonna walk back. If I measured all of those angles, 1, 2, and 3, their sum would be 180, right? Okay. We could test that. We could go out there and just walk 10 meters in some direction, walk, some other distance in some other direction, then walk back to our starting point. It would work, right? All the time? Yeah. Would you agree? I don't agree with that. I don't agree with that at all. Okay, let's say that we're gonna change things just for the sake of simplicity. We're gonna change things just a little bit here. Let's take a planet just like ours, just so we're not constrained by these messy things like land. We're gonna walk on a frozen ocean. So we're gonna pick a water world. This has got nothing but water, and that's. And so, and we're gonna have it frozen, and it's gonna say it's the same size as our Earth, but we're gonna take a longer walk this time. So here's our planet. Or here's our new planet. That's going to be the equator. Let's make that the North Pole of our new water world planet. So I'm going to start right here, and I'm going to walk in a straight line a long ways this time though. I'm going to walk like maybe clear over to there. So I'm going to walk like a quarter of the way around the planet. Okay, long ways. Wouldn't have to be that long, honestly. And then I'm going to turn at a 90-degree angle, and I'm gonna have like a little compass with me or some kind of a carpenter square, so I can I know I'm going at exactly a right angle, and I'm walking perfectly straight the whole time, right? I've got that ability. So I'm gonna turn and I'm gonna walk at a right angle north, and I'm gonna continue north until I get up to the very top of the. That's not very good. Let me draw that again. Until I get to the North Pole. Then I'm going to say, okay, well, when I'm there, I think I'm going to go ahead and I'm going to turn 90 degrees to the left again. Okay. Get out my protractor. I'm going to turn 90 degrees, so this is now a 90-degree angle. And I'm going to walk back down. And let's say, I'll tell you what, to make things a little bit different, I'm going to say it might be a little easier to see here. One little slight change. I started my journey right there. And so I'm just going to travel due north from there, get to the North Pole, turn 90 degrees, and head south again, right? So where am I going to end up? Well, I'm going to go down here, and when I get to the equator, I'm going to turn left again and make a right angle. And would you agree that after walking a while, I'm going to get right back to my starting place? Okay, so I made a triangle, didn't I? Yeah. I did, because I walked, I know that I walked for a fixed distance in a straight line 3 times. I only changed direction once, twice, and then I walk back to here, and I intersect, right? That's a triangle. That's the definition of a triangle, isn't it? If I add up all the sum of all the interior angles there, though, what do I get? 270. Well, that's not 180. You guys told me 180. Because the Earth's what? Not round, but spherical. Okay, so geometry becomes different, doesn't it? It becomes different and more complicated if our surface is not flat, right? Is that weird geometry? Well, maybe compared to what we've been doing, but it's just as useful and it's just as understandable, if you want to study it, as the kind of geometry we've been doing. So our geometry has been sort of flat geometry. And the term we use for that, flat works, that makes sense, but we also say Euclidean, because Euclid was a geometrist going way back to the long ago, and he's the guy that originally developed a lot of the stuff that we're learning right now. So all the things that we're learning, and I think I even said this at the beginning of the year, you got to take it a little bit with a grain of salt, because it's all pretty heavily constrained. All the stuff we're learning only applies on a flat surface. Once you tweak the surface, so it's either spherical, then you've got a new kind of geometry that's needed, right? You need spherical geometry. Spherical geometry, you know, at the end of the year, I'd like to take a little time and just introduce you to some concepts in spherical geometry. In spherical geometry, instead of talking about lines, you'd talk about what we call great circles. And it's a little different. The vocabulary is a little different. Much of it's the same, but obviously some of it's pretty different, right? There's another kind we could talk about. It's a little harder to draw, so I didn't do this, but in Pendleton, this ought to be easy to visualize. In Roundup City here, we're used to talking about saddles on horses. Well, a saddle shape is what we call a hyperbolic warping in math, right? So a saddle shape would just be a shape where it's hard to draw two-dimensionally, especially for me. But it's going to curve down like this in one direction, and then in the other direction, it's going to curve like that, right? So you're going to have like, it's going to go this way. It's like you take a sheet or something, and you're going to make it U-shaped, and then you're going to take these corners and you're going to make them U-shaped the other way, right? That's a hyperbolic shape. Hyperbolic shapes do the opposite. If I took a hyperbolic shape and I made a triangle, what do you think is going to happen to the sum of the interior angles compared to 180? Small. It's going to be less than 180. Yeah. Yes, sir.
So it's just the same shape.
Yeah, kind of like a Pringle. Yeah. Yeah. Exactly. Or a saddle on a horse. Okay, so why do I bring this up? Well, it's going to be relevant, and you're going to see why. We're going to change topics again, and eventually we'll pull all these things together. So I want to ask you, in how many dimensions do you perceive the world? We live in a three-dimensional world, right? Three extended dimensions. Imagine this. Any basketball players in here? Kirk plays basketball. I know Kirk. Okay, so Kirk, you're going to be the victim of our experiment here, right? You won't actually have to do this, but we're going to use you as our pretend victim here, or subject. Imagine that we took you and we put you in a, not painful, but we put you in a mechanism that immobilized your head so it couldn't move, okay? And we gave you a basketball and we put a hoop in front of you and you're going to shoot hoops, right? We're going to cover up one of your eyes to remove our brain's ability to have stereoscopic vision, which is kind of cheating. Because really all your brain does is it takes images from both eyes and it interprets that data in such a way that it can kind of gauge depth, right? But if you close your eye like this, if you close one eye and you look, it's be much harder to, for example, reach out and touch something and get the depth right with one eye than it is with two eyes, right? We have some other cues. Our other cues are things like, things get smaller as they move away from us. And we have a pretty good idea how big objects are supposed to be normally. And so our brains can interpret that information and say, well, I basically know how far away that is. But sometime, just try that. You have to do it now, but sometime just, when you're thinking about this weird talk we're having at home, just try doing that. Try, finding something that you can reach out and touch with two eyes open and then move around a little bit and cover one eye, and it's hard to get it just right. It really does make a difference. So we're going to fool Kirk here. We're going to put him in this contraption where we immobilize his head, and we're going to let him shoot some hoops on this basket with one eye covered up, and then we're going to he's in like a little booth, we're just going to put a blanket over the top, and we're going to change things a little bit. Unbeknownst to him, we've previously taken a really high quality picture of the basket that he's been shooting on, and we're going to roll the basket away, and we're going to move out instead a blown up version of that picture that looks from his perspective identical to the basket that he was shooting on before. Now if he can't move his head, and let's say, there are still some tricks he could do. He could focus his eyes and see that things aren't coming in and out of focus, but let's say that we've done something. We've maybe borrowed some optical drops from Dr. Monkman, and we've fixed his eyes so they're at a fixed focus. He can't change his eyes. He's just looking right at the distance of where the hoop should be. We're going to pull this cover off, give him the ball again, and what's he probably going to do? We're going to say, okay, let's see how many you can make.
Probably not shoot.
He's gonna, from his perspective, it's gonna look identical to the way it looked before. He's just gonna shoot, he's gonna be surprised that the ball's gonna bounce off the wall instead of, there's no basket there, right? He's not gonna know any different though. Would you agree that that could happen? Kind of an elaborate setup, but my point is just this. All that setup is just to demonstrate that we are perceiving the world in 2 dimensions. We use these tricks, our brain does, to be able to conceptualize our own local universe in 3 dimensions. Like I know, as I walk across the front of the room here, I can see the students in the front row are moving through my field of vision faster than students in the back. What's that telling me? They're closer, yeah, they're closer, aren't they? Even with one eye, I can see that, and so I can gauge, and I also see people are smaller in the back. You guys are all basically the same size, so my brain's pretty smart. I know Duncan's further away. And so if you remove a lot of these cues, you remove the ability to kind of move your head around and watch how things react, you remove your stereoscopic vision, what we really are doing is we're seeing 2-dimensional pictures and we're reconstructing those to understand that we live in a 3-dimensional space. Even though I can only see things in 2 dimensions, I have a pretty good idea of what it means of behind this and in front of this, right? I know that okay, I can see over here that, Alex, he didn't really just disappear from reality. He's just behind Matthew now. I know that. I know if I walked over here, I could, oh, there he is. Yes, he's there. He didn't disappear. I know that stuff because my brain is smart enough to understand that this is 3-dimensional and I can string together these 2-dimensional pictures. Okay, big deal, right? Well, it's a little easier to see if I introduce you to some of my friends. Here. My 2-dimensional friends. This is you. Yeah. Okay, so you may not have known this all year, but this whiteboard up here, this Promethean board, is really just it's a piece of a 2-dimensional universe populated by 2-dimensional creatures. For example, let me introduce you to a couple of them. Here is, there's Mr. Blue. Okay. Here is Mr. Red. And what other one can I do? There's I'll do Mr. Black.
Oh, that's.
So these guys are 2-dimensional creatures. They live in flatland up here on my board. Their universe, unlike ours, has only 2 extended dimensions, right? So it's very difficult for us to imagine how they perceive their universe, but we're going to have to try a little bit. Try to if we're going to understand this talk, we've got to sort of understand how they see their universe. What does their universe look like from our perspective? If we immersed ourselves in their universe, it'd be pretty boring to us. What would it look like? It's flat, sure.
Could be nothing. Wait, which way are we in it?
Well, say that we shrunk ourselves down to 2 dimensions, and we were looking around in this universe. How would I see Mr. Red?
As a line.
As a line, as a segment, right?
Yeah.
Yeah. When I look out there, I mean, when I see Emma as a 2-dimensional cutout of her shape, right? That's going to change as I walk around her a little bit, but it's 2-dimensional. Now I know it's really 3 dimensions. I know that she's got some depth too, but I only see 2 dimensions at a time, right? They do the same thing. Now think about how we could sort of pare down our complicated universe to their easy one. We live in a 3-dimensional universe. We see things in 2 dimensions, but we can piece them together to understand that there's actually 3. They only have 2, right? They live in a 2-dimensional universe, which they're smart. These flatlanders are smart. They get it. They do flat geometry just like we do geometry in their flat classes, and they know that it's 2-dimensional and they can travel up and down and side to side in their universe. But what do they see? How many dimensions do they actually see? 1. When Mr. Red looks at Mr. Blue, he just sees a blue segment, right? Difficult for us to conceptualize this though, because when we think of a blue segment, I bet you're visualizing, if if I put my eyes in the board and I look at Mr. Blue, I maybe see a blue segment and then it's black everywhere else, right? Above and below it. Does that make sense? Is that how they see it? They don't know what the other dimensions are. They don't see it that way, right? Right? We look out there from our perspective. If I kind of look into their plane, I would maybe see something like this. Like, let's say, here is their, oops. Here is flatland. I'm sort of looking through flatland, and there's this dark blue segment that corresponds to Mr. Blue. And then up and above and below would be just maybe black or something, right? We don't know, because we're only, but they would never know that what we would call above and below the plane. What's that to them? They have no idea. That'd be some bizarre concept of some extra third dimension that they would have no clue how that could possibly work. They have nothing relevant in their frame of reference to even understand how that other dimension could be there. Everything they know, everything they've been taught, everything they've observed has been limited to being inside this two-dimensional plane, right? You get the idea? But they get it. I mean, they get that if Mr. Red is having a conversation with Mr. Blue, and oh, hey, Mr. Black, how's it going? Mr. Black walks behind him. Mr. Red is going to see Mr. Black disappear for a second as he walks behind him. That's normal. He'd say, oh, well, you just walk behind him. That's fine. He gets it, right? He understands how the two dimensions work, okay? Now, why do I bring all this up? Okay, so
You're really in the circles.
really in circles, yeah. Okay, so now, what do you think happens when their teacher, these guys are students, their teacher in their flat geometry class, their flat honors geometry class, gets up there and drops a flat pen, and it falls, just like it does in our round universe, right? And he asks the question of these people, these flat people, what just happened? Well, they have the same answer you guys did. They say, well, we studied our flat physics. We know that that's just gravity, right? Because the flat world that they live in has some mass, and then when they, we drop that flat pin, it's attracted to the mass of their flat planet, right? And so they see something fall also, right?
There's no way. It wouldn't drop. It would just be a thing, and they drop it.
Okay, well let's say this. Let's say,
Yeah, there's no height.
okay, yeah. To make this a little bit easier, let's say, for example, that
Fall inside.
I think what he's trying to tell us is we're all just a bunch of circles.
not exactly. So let's say that this is a flat star in their universe, right? So there's my flat star. If we have a flat marble up here that we're going to drop, and the flat marble is going to accelerate into that star.
Oh, well, that's nice.
Okay.
That's a very nice thing for somebody
Because
to
of
do.
flat gravity, okay? But they have no idea what the flat gravity is, just like you guys did. Okay, but I'm going to fill in a blank now. When I drop this pin, I'll tell you what's really happening here, and this is the honest to God truth. I am not making this up. I am 100% certain about this, like every physicist would be. What's happening when I drop this pin, yeah, it's gravity, but what's really happening is this pin is falling into a four-dimensional gravity well. That's really actually what's happening. Four dimensions oversimplifies it just a little bit.
Whoa.
For the sake of argument, I'm going to call it 4 dimensions. It's a little bit more complicated. It's actually probably, you have to say 6, but that's irrelevant.
No.
The point is, though, it's falling into, this is all I need you to know, it's falling into a gravity well that we can't see, right? We don't notice that, right? We don't notice that there's a gravity well there. Everything looks normal to us, but it is. This thing is literally falling into this well that's created by the Earth. The Earth creates a divot, like a 3-dimensional divot, in the space-time continuum, right? Space-time. It really does. And this pin falls into it. Who told us this? Anybody know?
You?
Einstein did, that's right. Einstein told us this, and we just passed the 100-year anniversary just recently, like a month ago or less.
Too much.
How does it fall?
I'll tell you, we're going to keep talking. We just passed the 100-year anniversary of when he he published his work called General Relativity that explained all this to everybody. And nobody bought it at first. Well, this will help you understand it a little bit. Okay, so now we can't see this, right? Because the well is not, it's a warping of our three-dimensional space. And we just are stuck in the 3 dimensions. But fortunately for us, if we look at the same phenomena in flatland, we can see it. Okay, we can see it because we are higher dimensional creatures than they are, right? They're stuck in 2 dimensions. And so when they drop this marble and it falls towards this flat star, they don't see the well, but we would. What's actually happening here to us, from our perspective, what we would see is that if we turn flatland like sideways, so I'm going to take this plane and I'm going to turn it like this now, let's imagine, right? So say it's like the surface of a flat mattress, okay? When it's falling into this gravity well, to us, that would look like a divot in the flat surface. So imagine you've got a foam rubber mattress. We've got it's perfectly flat. I put a bowling ball on the foam rubber mattress, and what does it do? Yeah, it sinks down and creates a divot. So if I drop a marble on the bed, and now all of a sudden I put the bowling ball down, what's the marble going to do? It's going to roll into that divot, right? That is exactly what's happening in flatland. With their flat gravity is that divot. Now, can they see the divot? They can't see the divot, right? Because think about this. Our eyesight, for example, when we look at light travels straight, doesn't it? Right? So I know that there's Matthew right there. I can see there's his eye right there because the light is traveling in a straight line to my eye, right? So in our universe, these divots created by gravity, the light is affected by the shape of that space in a way that's invisible to us because the light is still going to travel through the space. Even if the intervening space has been warped a little bit, we're never going to know because as far as we're concerned, light travels in a straight path, right? They're going to see the same thing. So when they look, if we're going to look in profile as our, we're like gods to the flatlanders. We can see things in extra dimensions. So we can take their universe and flip it on its side, and then it just looks like this, right? Just looks flat, right? Now, when you put this bowling ball on the mattress, or maybe it's a flat black hole in their space, then it's gonna warp this down a little bit. It's gonna start to look like that. Right? Now they wouldn't see this. They wouldn't see this because from their perspective, the light rays, like let's say that there's some pink object over here. The light rays from that pink object are just going to travel through their space over to them. Okay. So they're not gonna see, they can't visualize this depression, but what they're gonna see, there are gonna be some noticeable effects. There are gonna be some effects that they're gonna be able to look at this and say, okay, something strange is going on here. We can't see this divot, but it must be there. Flat Einstein is the guy that figured it out in their universe. Here's what he did.
There's probably like a mystical way out.
Is there more than one divot?
Well, yeah, everything that's got mass is creating a divot, right?
We are 8 dimensional.
Okay, so there's the flat black hole, right, in their space. Now, what's going to happen? So here's Mr. Blue down here.
Yeah, I know.
Hold on. Mr. Blue is, and let's not make this a black hole. I'm going to make this their sun or their star or something, right? Say it's their sun, so it's pretty close.
Wait, so is that not the divot?
It is. It's creating a divot. On the other side of their star, Mr. Blue loves to gaze at the stars. Mr. Blue is out. He knows, he looks at the flat astronomical tables, and he knows that, because we can do this, we can predict where every star is going to be at any time in the future or the past, right? Because they're relatively stable, but we know how the Earth rotates. We know where we are in the solar system. We know that if we know it's part of our galaxy, we know how the galaxy's changing, so they can make these predictions. They know that, like every night at this time, he looks at his favorite star up here. Well, okay, but here's the deal. Mr. Blue it just so happens that this is a day of an eclipse. And he's going to look by, and the flat moon is just blocking the light from this perfectly, just like ours does. Conveniently, our moon just covers up our sun. And he's able, because it blocks that light, he's able to look by his sun. And he knows that his star shouldn't be visible right now because the sun is exactly covering where it should be. It should be hidden behind, let's say this is his star right here. His star should be right there. It should be behind the sun. But he looks by the side of the sun, and all of a sudden he sees that it's not there. It's migrated. He sees it as being right there instead. So I'm going to make it a different color. He sees it as being right there. How come? He sees it as being there because the light rays have been bent. These light rays that are leaving this star, because the space has been warped, the straight line is no longer straight. The straight line has been changed because the space itself has been warped, and the straight line does that from our perspective. Okay? So what does he see? He sees the same thing we see. When we look at stars that should be hidden behind the sun during a solar eclipse, or for weird reasons, they're not there. They're not there. You can look right by the sun, if this happens. You can look right by the sun and you can see a star that should be hidden. Has the star moved? Of course not. Of course the star hasn't moved. The star is light years away. It has a huge mass. It hasn't been physically moved through space. Has the light been bent in a way like a lens? No, it hasn't. That's not it either. That's not it either, because, now, I'll tell you why. This gets a little complicated. Does light have any mass?
Okay.
Light does not have any mass, right? Light has no rest mass, and only objects that have rest mass are affected by gravity. Light is completely unaffected by gravity, in the way that if I throw a ball to somebody, it's going to arc through the air, and they're going to catch it, right? Why does it arc through the air? Because gravity pulls on it, and it bends its path. That doesn't happen with a laser. If I shoot a laser in that direction, it's not going to bend. It's going to travel in a straight line, isn't it? Even though the Earth's here, right? So it's not that it's been bent gravitationally. It's not that it's gone through a lens. It's nothing like that. What's really physically happened is space has been warped and reconfigured itself in such a way that there is now a straight line path to that star that wouldn't have normally been there if the sun wasn't there. Okay? If the sun didn't have any mass, if we removed the mass from the sun and did the same thing, that star would drift back, the universe would reconfigure itself so we couldn't see the star anymore. It would unwarp, right? If the universe were just or if the sun were a great big piece of ultralight styrofoam instead, we'd look by the edge of it and we couldn't see the star. But because it has mass, it reconfigures space in such a way that that straight line does connect us to the star. That really happens, by the way. It's measurable and it really happens. Everybody thought Einstein was a kook until people started to measure some of his predictions, and they all turned out to be right. In our solar system, so here's our sun. What's the closest planet to the sun?
Mercury.
Mercury. So there's Mercury. Mercury is really close to the sun. What's next?
Venus.
Venus. So then Venus is out here, and then Earth is out here, right? Okay, and then it keeps going.
And then Jupiter.
So we know the gravitational mechanics that tell us where the planets are is really simple, really, really simple. I mean, it's not. You could really even, I mean, in high school you could use the laws of universal gravitation and make a very accurate prediction where Jupiter is going to be in exactly 1,095 years and 3 hours. It'd be easy to do. I mean, and it's going to be accurate. We can do that for every planet, but it doesn't work for Mercury. It doesn't work. Mercury, when we use these normal calculations, and we decide that after a certain amount of time, let's say Mercury's gone around the sun, when it should be there, it's not. Turns out that it's actually like right there.
So
It's a little bit ahead of where it's supposed to be.
are all the planets in the sun's exhibit?
They are. That's why we move. What would happen? Okay, imagine this. You guys have probably seen. Where would you see this? Like sometimes at like a place where you'd go and there'd be lots of games, like at a carnival. Have you ever seen those, or like things with coins, where you roll the coin in and it goes around that big funnel and then it falls in the middle? So if you play games with this kind of stuff, if you shoot a marble into this cone, what happens to it? Doesn't it just kind of move in a circle, right? Around the outside of this thing at some height. You get what I'm saying? I'm saying it kind of clumsily, but you got a big, huge cone, and we're gonna roll a ball around this big, huge cone. Because there's one of these at a water park too. Right? Yeah, you've seen these at water parks, like you come shooting out and you go around this big funnel and then you go down the funnel. Yeah. Well, you travel originally in a circular path. How come? Because you've got some tangential speed that prevents you from falling into the middle, right? But you're being pulled towards the middle, and so it bends your straight line into a circle. That's what's happening with our planets. Our Earth is like one of those marbles that's rolling around this divot in space, and that's why it travels in a circle, right? Okay, well, yeah. Now, why do things eventually fall? Why do you eventually fall through the hole in the middle at the water park? Well, okay, but there's something that's going on there. Okay, yeah, you lose your inertia, you lose your speed. How come? Friction with the surface, right? Okay, how much friction is there affecting the Earth? Very, very little, and it's got a huge amount of inertia, right? And the only momentum that it loses is due to when it just bumps into, interstellar dust and, stuff that's hardly going to make any impact on it at all. So the Earth just keeps doing this, right? It's not really ever slowed down. But you get the idea, right? Okay, so why does this happen? Mercury is supposed to be here, but the calculations say it's supposed to be here, but it actually ends up being there. How come?
Would that mean that someday the Earth is heavy mesosphere exploding because of the way?
Well, for various reasons, yeah, eventually. I mean, I'm getting off on a different. Ask that one later, because I've got a good answer for you. But I don't want to get off topic right now. Okay, here's why. Imagine a basketball. Okay, let's say that we're going to take like a rubber circle, flat rubber circle, and we're going to push it down over the top of the ball. It's going to stretch a little bit, right? So it's red, so we can see the difference between the two. But we're going to take this red rubber circle and we're going to stick it on the top of the ball, and then these are just like lines so we can see the stretch that connect it to the North Pole, right? Now, if I measure the distance around the perimeter of this red circle, that's what we might call circumference, right? Yeah. We know that, and we haven't talked about this yet, but you've probably done this in past years. If I take a circle, the circumference of the circle is related to the radius how? Circumference C equals, do you remember? No, that's area. Say it again.
Are one students to be dismissed at this time? Are one students going on the field trip need to be dismissed at this time?
Okay, that is the relationship between the circumference and radius in a flat space. Now, when I pull this flat rubber circle down over the top of the basketball and it stretches a little bit, say the circumference stays the same. Okay, as it was when it was flat. Maybe it's got a wire in the outside, so it stays the same circumference. What's happening to the radius? Here's the radius now goes from there up to there. What happened to it? Did it get longer or shorter or stay the same? Longer. It's a little longer, doesn't it? So in a non-Euclidean, in a non-flat space, in a spherical space, and that is what gravity does. It warps the universe spherically. So in a spherical space, the radius now doesn't fit the circumference anymore. The radius is too big, right? So we can see the radius, we can measure the radius between Mercury and the Sun, but what we're seeing is it'd be like looking down on this stretched circle from above. We're seeing the flat version, right? We're seeing this distance, but when we stretch it down, it's actually been extended a little bit. And so the calculation that we used to predict the position of Mercury was inaccurate. We were using regular physics when Einstein showed us that we need to use general relativity. We need to use higher dimensional physics to understand that, right? And so that's why there was this discrepancy. Now, what do you think happened when we took Einstein's equations and plugged them in? It was exactly correct. And that's the first time people started to say, okay, this crackpot may be onto something. I mean, it made these predictions that were exactly right. And there's all kinds of, tons of other predictions that we've done and tested since then that also work. Like, for example, the radius of the Earth doesn't match its circumference. It doesn't work. If a satellite is orbiting around the Earth, the distance it travels, which we can measure with GPS, is different than how far away it is from the center of the Earth. It differs, but not very much. It differs by like 13 centimeters, but it's predictable and it's measurable, and general relativity gets it right. Okay, so you start to get a little bit of a conception of what gravity is then, right? So when I drop this pin, what's it doing?
Warping the space.
Yeah, it is. Now, we can't see the well, just like the Flatlanders can't see their well, because you can't see tweaks within your own, how do I say this? Within their two-dimensional universe, they can't see the warping into a third dimension because the third dimension is completely foreign to them, right? They don't have access to that. They are two-dimensional creatures, and so they only get 2 dimensions to live in, right? That third dimension is transparent to them, but to us, three-dimensional creatures, we could see it. Yeah.
Could a person, if someone lived in a four-dimensional world and came here, could they see everything?
Exactly. So if somebody lived in a four-dimensional world, in fact, in four-dimensional honors geometry class right now, they're having the same discussion. And they're talking about us simple little, like spherical landers. But those guys don't get it. They just don't, they can't conceptualize this fourth dimension, right? For us, and okay, now think of it this way. Here's the last thing. How much time we got? Oh, okay. All right. Take 5 minutes tomorrow, and then you guys will do something different.
So like the warp is a shape. Like what shape would you do that?
You can't imagine.
All of that just gravitational lines in general.
Yeah. Right. Okay.
I found it all very fascinating.
It is. Oh, it's good stuff. It's good stuff. All right.
Yeah, that's also kind of what I plan to do in this field.
Oh, cool.